But then you do get some project teams which score perfectly. The best student I ever had in IDL got 103.5 out of 105, including the bonus points. His name was Derek, and this was in spring 2020, and his performance was so extraordinary that I still remember it. All right, morning everyone. Let's begin. Please shut your laptops. The attendance slide. Why is it that there's nobody in class? And it's barely, we're not even halfway through the semester. The days are getting longer, right? It's cold? It's not really cold. It's February, right?
Well, it's not cold for February, but it's subject.
I think it's getting to the final of the semester. People are getting tired.
Okay, all right, guys, shut your laptops. If you have your name tag still, please get them out, and let's begin. We're going to finish the bit on training networks. And so we're going to be talking about the final bits of training, right? So what we've seen so far, we've seen that shift invariant pattern classification tasks are such as does this picture contain a cat, or does this recording including hello, are best performed by scanning for the target patterns. And scanning is the same as using shared parameter networks. May I remind you that at 7 p.m. Okay, guys, if you're done with the polls, shut your laptops, right? Yeah. Okay. These are shared parameters that parameter networks that can be trained using variations of Backprop. And so for Backprop, the way we saw it, we would pass the data instance through the network. Now we are going to take into account that this is just a shared parameter network. We're going to actually compute a divergence between the actual and desired outputs of the network, then use standard backpropagation rules, and then propagate the derivatives backwards through the MLP, and then we made changes for the back. We had to make modifications for both the convolutional layers, which included the final activation as well as the convolution operation itself. So given the derivation for the final, the derivatives for the output activation maps, we had to compute the derivatives with respect to the affine maps. And then given the derivatives with respect to the affine maps, we had to go back and compute the derivatives with respect to the filters and also with the previous layers outputs. And then we need similar derivatives for the pooling layers. Given the derivative with respect to the output of the pooling, how can we compute the derivative with respect to the input? We took a quick look at this. If you want the derivatives, backpropagate the derivatives from the output activation maps to the affine maps, that was easy. We're speaking of backpropagating derivatives from here, from y to z, and that was obtained simply by a pointwise update. You multiplied the derivative at each y by the derivative of the corresponding activation function that transformed the z to the y. So that was done. And then we also saw how, given the derivatives for the z's, how we could backpropagate them all the way back to compute the loss derivatives for the previous layer and also for the filters. And for the loss derivatives for the previous layer, we just saw that this just ended up being a convolution, right? We pulled out to compute the derivative for any given input channel to the layer. We pulled out the corresponding channels of all of the filters, transposed them, which was flip them left to right, top to bottom. Then we zero padded all of the output channels or the derivative maps for all of the output channels and then convolved them with the transposed filter. And that gave us the derivative map for the input channel. This we saw. And we also saw how we can compute the derivatives for the filters themselves. All we did was convolve to compute the derivative for any particular filter. All we did was convolve the input channels, the entire collection of input channels, with the derivative map for the affine output of that filter. Here there was no transposition or any kind of reflection involved. It was just a direct convolution. And that gave us a derivative for the filter itself. So everybody remember all of this, right? And so we've figured out how to carry the derivatives back from here all the way to the input channels through the filters too. So that leaves us with derivatives for the pooling layers. Now here's a principle that I'm going to state, and this is something that we have to remember, that anytime you have any kind of a process, it doesn't matter what this box is, whether it's a convolution, upsampling, downsampling, pooling, what have you, the input is of some size, and this goes through this box, and it results in an output of some other size, which might be larger or smaller. And of course, eventually, this results in the computation of a loss. So when you compute the derivative of the loss with respect to the input to this process, the number of elements in the derivative is going to be exactly the same as the number of elements in the input itself, even if it's downsampling, right? Because every one of these terms potentially influences the loss. And so perturbing it potentially modifies the loss. So if when you backpropagate the loss derivative, the gradient, which is again the transpose of the derivative, right? But we're going to be speaking in terms of gradients. If the gradient is not the same shape, if the gradient at any position is not the same shape and size as the original variable itself, you have made a mistake, right? This is a principle we're going to keep using. Okay, now here's how we performed pooling. We just sort of stepped left to right, and at each point, if you were performing max pooling, you found the index of the largest value and copied it over, right? And the output. So now, if I want to compute the derivative, I'm going to assume that the stride is 1, right? If I want to compute the derivative, I've got to figure out how to compute the derivative for pooling, right? Max pooling. And now imagine that I have some pooling window of this size, and I found found which is the largest value, and let's say this guy is the largest value. The output of the pooling is going to end up in some location in the in the output channel for the pooling, right? So when I'm computing my derivatives back here at this location, I would have computed some derivative for the loss with respect to this guy. But then I must go and ask myself, which of these four elements actually influences the final loss? Which one influences the final loss? Just the maximum. Do the rest of them have any effect on the final loss? No, right? So what will the derivatives out here be for these guys? They are going to be 0. Now, what about the influence of this term on the loss? Yeah.
The value of the derivative.
Is it 4 times?
Yeah.
What happened when I actually performed a max pooling? Did I scale it?
No.
I just copied this exactly out here, right? If perturbing this guy by epsilon has some influence on the output of the loss, how much will perturbing this guy have? Exactly the same, because I just copied this value. Yes. If I perturb this by some delta x, there's going to be some effect delta L over here. And that's going to be the same as this one here. So what I would need to do is simply copy this back into the location of the max. Right? Make sense? So that's it. So back propagating through a max pooling layer is very simple. All you'd have to do is literally copy the derivative back to the location where the value was copied from, because that is the only value that's going to influence the loss. And the amount by which it's going to influence the loss is the same on both sides, because you basically copied it without any scaling, right? Make sense? Right. And so you have, that's how you can you shut your laptop?
Attendance.
Okay, so go ahead. So if you are actually performing the max pooling, remember, going forward at each location, you're just picking up the index, the location of the max. And this is why we needed the location of the max. We needed to know where to copy the derivative back to, and then read the value from the at that location. So going back, all we would do is increment the derivative at that location by the derivative at the location that it got copied to within each window, right? So why is there a plus equal to over here? Why does this have a plus equals? Anyone? Yeah. Right. So I might have, for instance, if I'm sliding forward, if this is my input, for this location, this guy might get copied over, right? In my output. And then when I slide forward by 1, the same guy might get copied over here as well. So I have this one location being copied into, potentially being copied into multiple locations at the output. And so when I go back, the derivatives from both locations must be summed in, right? That's why you have the plus equals. Okay? So for mean pooling, okay. So that makes sense to everybody? Right. Now, if I'm performing mean pooling, what happens? For mean pooling, what I would get over here is going to be the average of these 4 elements, right? So if I if I get some dl over dz out here, what happens? What is the corresponding derivative that gets back propagated to each of these in this case? Each has a contribution, but 1/4, right? Because each one of these is contributing equally to this one. So you're basically going to be, they have equal contributions to this location. And so going backward, the derivative, the arithmetic is fairly straightforward. That is 1/4 times the input value. Going back, the derivative is going to be multiplied by 1/4, right? So in this case, if I'm performing mean pooling, that derivative at the location that it got copied to is going to be uniformly distributed over all of the locations that contributed to the value. Make sense to everybody? Right? Very easy. Nothing fancy. And so if I were to write code, same thing. Going forward, you'd be computing the mean at each of the window at each location. Going backwards, I just take the derivative that I got at the output and divide it by the number of elements in the window, which is 1/k², because the window is k cross k, right? And distributed it equally over all of the cells that contributed to that pooled mean. And in fact, if you look at it carefully, mean pooling, the derivative for mean pooling is actually also just a convolution. So you would, for instance, pad, in this case, if my mean pooling user uses a 2x2 window, then I'm going to pad 1 column of zeros and 1 column of 1 row of zeros on either side of the derivative map for the output, and then just convolve it channel-wise with a uniform filter, right? It's like just an averaging operation. So as it turns out, mean pooling is the same going forward as it is going backwards. Once you just pad the derivative map, and you need to pad it just to make sure that when you go back, the derivative is the correct size, right? So in fact, if you're performing mean pooling, then the backward and forward code are going to be identical. Going forward, you'd actually apply it on the channel. Going backward, you're going to just zero pad and apply it to the derivative map. In fact, so code-wise, it's even simpler, right? And so we've sort of looked at the how to compute derivatives of the pooling layers as well. Any questions? No. Okay, who's line bear?
Oh,
Your line bear. What's the answer to the first one? Okay, and who is apricot hummingbird? That's interesting. There's an apricot hummingbird in class. Who is apricot hummingbird?
I am.
What's the answer to the second? True. Okay. So does everybody agree that both are true?
yes.
Thank you. Right. So when back propagating through a max pooling layer, derivatives from the pooling output back propagate only to the position of the largest input within the pooling window for that output. And when you're back propagating through a mean pool layer, derivatives are distributed uniformly over the input window. Very easy, right? So we've sort of figured out how to back propagate through the two main components of convolutional networks. One is the convolution itself, the other is pooling. But then you have a few more operations, the upsampling and downsampling. Upsampling and downsampling layers can increase or decrease the size of the map. And we saw that upsampling followed by a convolution can be represented or described as convolution of the fractional stride. And convolution followed by downsampling can be thought of as convolution with a stride greater than 1. Same thing for pooling, right? So how do we back propagate through these layers? Now, here's how downsampling happened. When you were performing downsampling, okay, you guys can help me out here. We had some input, and let's say we just had 1, 2, 3, 4, 5, a 6 cross 6 input, and I downsampled by a factor of 2. What is the output size going to be? It's going to be a 3 cross 3, right? Now, when I compute the derivatives for the loss, the gradient coming back, what is the size of the derivatives out here? Out there? 6 cross 6. It must be 6 cross 6, correct? But then these guys did these guys contribute to the derivatives?
No.
Okay. Because they had no contribution going forward, right? So because they had no contribution going forward, perturbing them has no effect on the output. Therefore, the derivatives must be 0. So if I'm going back, what do you think I'm actually doing with these derivatives? So I have these, right? I'm just blocking them out so that you can see how it goes. So these were the only values that remained, the ones that were not blocked. How do those we know that these blocked values have 0 derivatives. What about the rest of them? What happens? This is Since this value is identical to this value, whatever derivative you have over here is just going to go here, right? This value is identical to this value, whatever derivative you have over here is simply going to go here, and so on. Make sense to everybody? Right? So backpropagating through a derivative layer is going to be very simple. I'm first going to allocate an input. Now observe something interesting, right? When I backpropagated, when I went forward, I lost this last row, right? Is there any information that I've lost the last row in the output?
No.
Right? If I hadn't had the last row, the output would have been the same size, right? So how do I know that? So does that mean when I backpropagate the input, it's enough to compute a 5 cross 5? Yes or no? Can everybody say no?
No.
Why not?
Because the shape of the input won't be the same as the...
You want the derivative to have the same size as the input, correct? And so where do I get this extra information from? Pardon me? So the previous layer, you're going to have to save this information somewhere, right? You're going to have to know how large the input was. When you're performing any kind of downsampling operation, you're likely to lose things at the boundaries, right? And you're going to have to also, now, do we have any information whether it was the row lost was to the right boundary or the left boundary? Do we have any information about that?
Yes.
How?
Because it's never going to be the left boundary.
Why not? You're just dropping every second thing. You could have chosen to drop the first s minus 1 and then picked up the s, right?
But it's going to be consistent in both.
So for the consistent, you have to keep track of that information. The output by itself doesn't have that information. Whereas in most other operations, when you don't have any kind of resampling, when you look at the output, you know pretty much exactly where in the input it came from. But for downsampling operations, you have this craziness that you do not know whether you've lost things at the boundary, and if you did, you don't know which side you lost it on. This information has to be retained as part of the downsampling operation itself, or it has to be inferred, right? And so when you're actually computing the derivatives, you're going to have to first allocate the derivative map of the right size, and this size is not evident from the output, correct? And you're going to have to figure out which boundaries are padded, if any. And so once you fill the derivatives in those locations out with zeros, then you can just copy the values over, right? And that's going to be the derivative map going backwards. Now, what does this look like? It's just upsampling. So the derivative for downsampling is upsampling. But is it exactly upsampling? Why not?
Because it depends on the shape of the input.
So it is not exactly upsampling because, again,
It can't be random.
no, you have to deal with the boundaries. The only issue is with the boundaries. If you didn't have boundary issues, then the derivative for downsampling is upsampling. And what do you think the derivative for upsampling is going to be? Downsampling. Those two are basically just inverses of one another, right? But they're not exact inverses because of the boundaries, right? So, but all we did was just copy these things over. That makes sense? It's a very trivial operation when you think of things this way, right? And so I have some pseudocode. If you're going forward, then when you're going backward, you just sort of pre-allocate everything and just fill in the stuff, right? Now the same thing with the upsampling layer. What happened in the upsampling layer? You went this way, right? In the upsampling layer, maybe you started off with a 3 cross 3, and then you just padded a bunch of zeros, and you got the upsampled value, right? Now, if you look at this location over here, does this location have any relationship to anything in the input? Yes or no? No, right? So will that have any influence on the derivative going backwards?
No.
Because there's nothing you could do to the input that would change those guys going forward, right? And so when you're going backwards, what do you think the derivatives for upsampling is like? What do you think they're going to be like? These guys contribute nothing to the derivative going back, right? What about this one? This is just a copy. So you're just going to be copying things, right? That makes sense to everybody? So the derivative for upsampling, you're just going to go literal. The derivatives for, when you go back, yes,
The shape in the previous slide is different from the shape before. Is that based on convention? What we choose?
so in the shape on the previous slide,
The extra row and extra column,
Yeah.
they differ.
yeah, there was 5 cross 5. Okay, you're right, right? When I'm upsampling, you're not going to have this guy. You would never upsample and put an extra 0 at the boundaries, which is why you have these boundary issues to deal with, right? And so, but again, so when you're actually going backwards, you are simply going to, when you go back, the derivatives, when you back propagate through the upsampling layer, the derivative will have the same size, the gradient will have the same size and shape as the input to the upsampling layer. So this is something, again, for the resampling layers, we have to keep track of the size because of the strange things that can happen at the boundary. And we know that none of these terms actually have any influence on the derivatives going backward, because when you were going forward, these terms did not depend on the input. You just filled in zeros. So when you're back propagating, you'll actually get non-zero derivatives in these locations. But they do not matter, because those inputs were just fixed at that point and had nothing, when we're not influenced in any manner by what came in forwards, right? And so the derivatives at these locations are simply going to be copied going back. And what does this look like? This is just downsampling. But then again, it's not exactly downsampling, and the only reason for this is the boundaries, right? Again, once again, you have to keep track of where each thing came from. This is going to be part of your standard upsampling code, just so that you know where to copy things into, right? So you know which ones to copy. You may end up copying the wrong ones. Yeah.
If you downsample with a stride of 2, will it look different?
If you downsample with a stride of 2, it's going to look the same. But the point is, downsampling over here with a stride of 2, and it's a shape issue, right? You don't know whether you're padding this 0 to the beginning or 0 to the end, or 0 at the end. So it's going to look the same, but it's not. The only issues are the boundaries. So for example, out here, if I gave you a just for to make things annoying, let's say going forward, you actually scaled things by a factor of 2. So if you scale things by a factor of 2, then this became you would have padded zeros out on the right and out at the bottom, right? And then when you're going backwards, do you know which ones to copy back? Again, that information has to be retained, right? You don't know whether you want to copy these 6 or whether you want to copy these 6, right? So knowing which ones to copy and such like is always going to be a bit of a logistical issue that you have to deal with. But otherwise, the concept is simple. When you're downsampling, when you go forward, you're just dropping every s minus 1 of every s rows and columns. When you're going backwards, you just introduce s minus 1 rows of zeros and s minus 1 rows of columns of zeros between every adjacent pair of derivatives. And similarly, when you're upsampling, you introduce zeros going forward. And when you're performing backprop, you just drop those guys. So up and down sampling are just performing derivatives, backpropagation through these resampling layers is really very easy, right? Now, typically, when you perform convolution followed by downsampling, the way you will implement it is not by convolving, and then downsampling. That's kind of inefficient. So what you would do is to just convolve with a stride of 2. But the problem with convolving with a stride of 2 is that if you think of convolution with a stride of 2 and then try to derive your back propagation rules, you're going to end up with funky stuff, because you're going to have to deal with adjacent rows and adjacent columns differently, because things are being dropped, right? So in this case, if you don't want to make your life miserable, then the simple thing to do is to just think about this as regular convolution followed by downsampling. And then we know exactly how to write back propagation rules through the downsampling layer, and exactly how to write back propagation rules through a convolution layer. So you don't have to write fancy stuff to deal with convolution with a stride. Make sense to everybody, right? And so this kind of back propagation is actually going to be much easier than trying to figure out how to directly back propagate through convolution with a stride of 2. Similarly, convolution with a fractional stride, right? If I'm performing convolution with a fractional stride, what happens? I'm actually upsampling and then performing a convolution. If you try to derive the convolution rules directly for this fractional stride convolution, you're going to find them to be rather painful. But then if you sort of recast them as upsampling followed by convolution with a stride of 1, we know exactly how to perform back propagation through upsampling. It's trivial, right? And so we can redo it this way. You can back propagate through a convolution with a stride of 1, and then back propagate through the upsampling layer. And this simplifies matters. Questions? No, okay. And the same thing. Pooling is typically done with a stride greater than 1. So pooling is often just called a downsampling layer, simply because when you perform pooling, you're going to reduce the size of the map, right? Like so. But then, once again, if you're thinking of pooling with a stride of 2, in the case of pooling, it might be simpler if you're just performing max pooling. For mean pooling, it's going to be a bit more painful, right? So if you try to back propagate directly through pooling with a stride of 2, you might find the arithmetic to be somewhat more painful than if you just decomposed it into pooling with a stride of 1 followed by downsampling. Yes?
So in all these slides, what is the kernel size you're taking? 3?
In this picture, it doesn't really matter, right? So it doesn't matter what the kernel size is. It's showing a 2 cross 2. But the basic idea remains the same, right? Nothing has changed. The stride has nothing to do with the kernel size.
If the kernel size is same as the image, then there is no downsampling.
If the kernel size is the same as the image, you're going to get 1 output unless you pad with zeros. But anything that you do, the general principle is going to stay the same. Remember, we discussed what happens at the boundaries previously, right? That you're going to lose n-1 rows and n-1 columns where n is the size of the kernel. And if you don't want to lose it, you want a 0 pad. So one of the things that will happen is that when you back propagate, you're going to get derivatives of the same size as the input. So if you 0 padded before you performed convolution, you're going to get derivatives for the 0 padded input. And then you're going to have to throw away the derivatives at the boundaries, because those things really were manufactured data, right? So, and as always, yes?
I had a question. In the previous slide, when we're pooling with a stride of 2 and say the kernel size is 2, that's a 5 by 5 grid. So for pooling stride 2, kernel 2, we'll need a 6 by 6. So do we pad the last row and column?
No, so for pooling, again, so the one thing, at each pooling, at each downsampling layer, you're going to have to keep track of what was the size of the input. That was it, right?
Okay, but I'm just asking for pooling with a stride of 2, not pooling and then down.
You would lose the last row typically.
Lose the last row. Okay.
Yeah, because zeros don't really add any information, right? So again, that's a design choice.
Okay.
So now, as always, code is simpler, right? So we saw conceptually, it's actually all very simple. but you had to understand some things. Now, if you don't want to waste your mental cycles on understanding things and you just want to be a software engineer writing code, you can still be just as effective a deep learning person. How so? You can just reverse the code. Now, we saw how backpropagation literally inverts the process of computation, right? So when you are going forward, you're just going for, you're sort of scanning, you're going through the layers. Within each layer, you're scanning the input. Then when you are scanning at each point, you first computed an affine term and then applied an activation. So when you're going backwards, you're going to do all of the loops in reverse, just as before. So here, for example, while this is a standard scan, right? If I'm scanning with just a stride of 1, when I did a backpropagation, we saw what we did, right? We inverted the indices of the loop, the order of the indices of the loops. And then here, whereas we were computing the activation at the end of the loop, we computed the derivatives for the affine term at the beginning of the loop, and then we just use the simple operation, right? We said y equals w times x. So dx equals y times dw, dw equals y times dx, was it? Yeah. Anyway, you got the idea, right? And so the same thing, if I'm doing this with a stride, nothing changed. If I'm doing this, when I'm doing this with code, when I'm looking at this through code, I would use exactly the same logic. When I'm going forward, my convolution is happening with a stride. So when I just flip the code to write the backward code, when I'm going backward, the convolution once again is going to happen with a stride. That's about it, right? And so you didn't even have to figure out the math. You didn't have to work out anything. You just redid the code. Questions? Right. So this would happen for pretty much every kind of operation, whether it's pooling or convolution. The point one is not open. All right, guys. Maybe you can just answer me, right? So give me some names. We don't actually have to answer the polls, but so there's an apricot llama. Who's the apricot llama?
It is
Apricot.
true.
It is true. Thank you. And second one, that's going to be the olive llama. There's another llama. What? This one's olive. Is the second one true or false? Olive llama. Olive llama is absent, yeah. And this is a bronze shark. So bronze shark, is the second one true or false? Bronze shark is absent. And there's an emerald leopard. So fancy leopard, is the second one true or false? Emerald leopard is absent, okay. Emerald owl. Where is the emerald owl? Is the second one true or false? Oh, okay, absent. Amazing. And olive seal. Who's olive seal? Olive seal is absent. Okay.
Oh, I'm here.
Okay, is the second one true or false?
It's true.
Okay, thank you. And silver owl. Who's silver owl?
Silver owl.
Okay, third one. Is it true or false? False. Thank you. Right. So everybody agree with those answers? Yes. Yes, Justin?
So why would the second one be true if technically you have to store the information in order to do it?
So the operation is the same. It's the only distinction lies in the boundaries, right? So that's all. It is a downsampling operation. It just, the details, the devil lies in the details. Somehow I seem to have misplaced my glasses. No, I haven't. They're on my face. Okay. All right. So learning the network, yes. Remind me, guys. I was searching for my glasses, right? We've shown how to compute derivatives for pretty much every component of the network. Right. So for the basic convolutional model, we could, in principle, go back and write the backward code without much effort at this point. And so here is the story we have so far. The CNN is a supervised version of computational models of mammalian vision, as we just saw 2 classes ago, going back. It includes convolutional layers comprising learned filters that scan the outputs of the previous layer, and downsampling layers, which are basically pooling layers. In the traditional literature, pooling layers were just called downsampling layers. And so just following the terminology, downsampling layers that operate over groups of outputs to reduce network size, right? Now, the parameters of the network can be learned through regular backpropagation. For if you're performing any kind of pooling like max pooling, the derivatives are propagated only over the maximum elements in each pool. The other pooling operators need an appropriate change of derivative rules. And for the rest of them, the derivatives must generally sum over sets of elements to account for the fact that the network is in fact a shared parameter network. And this results in some funky looking backpropagation rules. Now, so far so good. But the kind of, so what was the whole purpose of convolutional neural networks? The entire purpose was to have shift invariance in the model. So you wanted to be able to find out that the picture had a flower regardless of where the flower happened in the picture. But what if you wanted to be scale invariant or rotation invariant? I want to find out that if there's a flower in the image, regardless of whether the flower is small or the flower is big. Or whether, then how would I do this?
No, that's my question.
That is your question, right? Same thing. I wanted to find out if that there was a flower, but regardless of whether it was there at this angle or this one. Yeah.
Rotate or fit in the training.
So you can just modify your training data and scale your training data. But is that, if you want to account for this, what's going to happen to your model? You're going to have to, if you want to have to account for transformations, you can apply the transformations to your data. And then correspondingly, because now a flower which looks like this is not the same as the flower which looks like this. So you're going to have to learn more filters, more parameters to deal with every orientation of the flower. Right. Can we make the basic model itself scaling invariant or rotation invariant? How would we do that? Anyone? Yeah.
If you can implement some sort of like randomization into each layer, like
that's not. How does it introduce translation or rotation invariance? Any other ideas?
Maybe we can just rotate the derivative at the weights that we learned.
We can rotate the kernel, right? So if you want to look at these things, in your shift invariance, you had one standard pattern. And what you were really doing is making many copies of the pattern at each location. And so although I gave you one kernel, the actual computation had many identical copies of the kernel, one at each position, right? And that's how you got shift invariance. And now, if I wanted to have a transform invariance, what would I do? If I wanted to have an invariance that is be invariant to a 45-degree rotation, for instance, I can rotate my kernel and then scan with my rotated kernel, right? And so here, in the basic operation, here's what we had. I got out my cube. I just computed an inner product between the cubical slice of my data and my filter, which was a cuboid itself. If I want to be making it transform invariant, then I want to say that I want the network to produce the same output regardless of whether it was the flower in its original orientation or whether it was the flower rotated by 45 degrees, right? And so for that, I'm going to, what I can do is basically rotate the kernel itself by 45 degrees before I scan. And this is going to give me simultaneously a rotation invariance and a shift invariance, right? Yeah.
Would this be something you would only want to do in like not like the first convolution layers, but later when you're learning?
You would want to do this everywhere, right? So because you want to have all kinds of transform invariance. We don't do it. And you'll see why, right? So here's what is going to happen. So if I have a single filter and I scan the input, how many output channels is it going to produce? If I have a filter and if I scan the input, how many output channels is it going to produce? Just one, right? Each filter produces one. But then if I make two copies of the filter, one in its normal position, the one in the 45-degree rotated position, how many channels will it produce? Two, right? And now suppose I want to also account for a 42-degree rotation. What do I need? I need to have 3 copies of the filter, right? I need to have a different copy of the filter for every single transform that I want to have invariance to. And so here's what you would actually do. You're going to have to produce a set of transformed, you want to enumerate all the transformations, which could be scaling, rotation, reflection, what have you, and make one copy of the filter for every transform that you want invariance to. And then you're going to be scanning with each of those filters. That means that you're going to be applying all the various transforms out here. And so if you actually wrote down code, this was a standard code where you pulled out a slice and computed an invariant, computed a tensor and a product if you didn't want transform invariance. Now, in addition to scanning the input with the filter, you're going to actually scan the filter with every transformed version of the filter, which means that at each layer, the number of channels is going to explode. One per transform that you're allowing invariance to. Do you really want to do that? No, right? So which is why we don't do it. Which is why instead it's just cheaper to transform your data and throw in tons of augmented data and hope that, over the depth of the network, the model learns to be invariant to all of these rotations and transformations. But if you wanted to do it the formal way, here's how you'd have to do it. That makes sense to everybody? Right. And of course, if you perform implicit transform invariance, then when you're computing when you're computing the derivatives for any particular filter, you would actually compute derivatives for the transformed version, every transformed version of the filter. Then you're going to have to untransform those derivatives and pool them all to get the derivative for the original basic filter itself. And that's going to be a lot of painful work as well, right? I'll let you figure out how you do it. If you wanted to do it, I'll let you figure out how you'd actually implement those derivative rules. But then I'll leave you with the happy thought that we never actually do that, right? So, right? So, questions? So anyway, going back to our story, the models can be easily, the parameters of the network can be learned through regular backpropagation, right? Now, the models can be easily modified. I don't know where this bullet came from. I got to clean that out. The models can be easily modified to allow for different kinds of transformations. I should update these slides. I thought I'd fix them. Yes?
Why this approach can deal with the problem of the different size of the
Pardon me?
different size of sample?
Well, so again, you could do this by having different size of input or different size of pattern. There's a difference, right? So different sizes of inputs is just, it doesn't really matter. Yeah, it's scanning. So there's no restriction on the size of the input itself. If you want to be able to, if you want the detection to be scaling invariant, then you're going to have to either explicitly scale the filters or just throw in scaled versions of the data into your model, into your training. And the latter is going to be much more convenient than the former. Because when you begin introducing scaling invariance, you're going to have to worry about every factor of scaling, right? Okay. Now, yes?
We are going to be applying the same transformations to the val or test data as we do to the...
No, the test data is just, the test data, right? You just want to say, I want to be able to detect whether a flower has happened in the image, regardless of the size of the flower or the position of the flower, right? Now, in principle, you could have just used a simple MLP and just had lots and lots of variations of the positions and scale and sizes. But it turns out that when it comes to position, we can simplify matters by scanning, which gave us a CNN. Now, in terms of size, you can simplify matters by having the model itself be transform invariant, but that actually blows up the size of the model, whereas scanning reduces the size of the model, right? So therefore, for the scale invariance, you'd actually just modify your training data. Okay. Again, it's all about efficiency. It can always be formal, right? So now, here's the other thing. All of this, everything that we saw was trying to make the computation, the detection, position invariant, right? Which meant that you wanted to just find out if the image had a flower, and then you trained the model to just detect if the image had a flower. But then what if you actually want to find out where in the image the flower happened? Now, this would be easy if you didn't have a distributed scan. When we didn't have a distributed scan, you basically had a simple flower detector scanning the image. So you could find the specific locations where it fired and say here and here and here and here is where the flower happened, right? But once you begin distributing the scan, you have no idea about as to exactly at which level of the distribution the flower was actually discovered. In particular, if you have any kind of scale invariance to the, if you are in the model, right? Scalar transform invariance in the model. And so in that case, how do we determine where in the image the actual object happened? If we want to go beyond just saying that this has a flower, and if we also want to know where the flower happened, we're going to have to do some extra computation. And so here's how we would do it. The information about where the flower happened is actually in the final convolution layer already, right? And so in addition to just having a class output from the final convolution layer, which tells you which class of object happened in the image, you can have a second output which computes the corners of the bounding box for the object. And so this second one just be computing the coordinates of the bounding box. And then using the coordinates of the bounding box, you can define a loss, which is something like an intersection of a union loss, for instance, between the actual location of the object and the location of the object computed by the model. Now, for this, you would need training data in which the objects that you were trying to detect were actually kind of, the bounding boxes were actually given in the training data. And now you're going to have two losses that you're simultaneously minimizing. This is a standard multitask loss. And the model will learn not only to detect the classes, or to identify the classes in the, of objects in the image, but also tell you exactly where in the image the object happened. Now, if you have multiple instances of the objects, then you have to come up, then there are fancier versions of this where you'd actually be segmenting the image based on proposals. And then within each of those regions, you're going to be using the same technique. Right. Now, the same approach can be used for other things. For example, if you're trying to compute the skeleton. How many of you ever saw the spooky video we used to have at the end of the corridor that connects gates to, what did we have there?
It's the large TV which shows how much the rate is.
So no, but even before that, before we had this demo, we had something by Yasser Sheikh, which would draw these skeletons. You know, as people walked by, it would track you and just draw your skeleton on you. It was very spooky because it was so accurate, right? And so how does he actually do that? Eventually, I think people got so spooked that they made them change the demo. At least that's my theory. I'm going to stay with it. But how would you do that? It's very easy. I could actually have training data of this kind, where all the joins are marked. And then from the final convolution layer, I could just have the second predictor. The first one is going to detect if there's a human in the image or not. And the second predictor simply can simply predict the locations of each of your joins so that when you connect them up, you get a stick object, which captures the pose and the movement of the person in a video, right? So this poor person keeps coming back. So Bronze Lion, you're back on the scene. Who's Bronze Lion? Have I ever actually managed to successfully find Bronze Lion in class? Apparently not. Okay. Bronze Lion, you're absent. This one is new. There's a Red Tiger. Wait, was it Bronze Lion?
Yeah, I'm Bronze Lion.
Okay, what's the answer to the first question? Thank you.
I think the first question is true.
All right. Okay, since you're here, what about the second one?
I think the second one is also true.
Also true. Is the second one true, guys? Yeah, CNNs are invariant to the position, but not orientation or scale of the target pattern, right? They have to be made so. And now Red Tiger. There's a Red Tiger in class. We have a proper zoo, but then the zoo is mostly empty. Okay. There's a Bronze Bear. Who's Bronze Bear? Bronze Bear is absent. Okay, guys, Bronze Bear, last chance. Okay, there's an Olive Bear. We're going through the bears, apparently. Who's Olive Bear? There's no Olive Bear. Too bad. All right. There's a Coral Hummingbird. Who's Coral Hummingbird? Yes. The third one's true. Thank you, right? So if you check the answers to these, to find the position of an object, we need multiple output layers after the convolution. One to identify the class, and the second to detect the corners, the bounding box for the object, or the joints if it's a stick human being or whatever. And CNNs are invariant to position, but not the orientation or scale of the target pattern. So they must be, if you want to explicitly introduce scale or rotation invariance, you're going to either do this by manipulating the training data or by actually introducing this in the form of transforms of the kernels. And so to make them invariant to a transformed versions of every filter must be introduced, which can be quite a pain. So that pretty much goes through everything we wanted to cover in CNNs. So there's just some final wrapping up. You have other variations. You can have very deep networks. You've all worked with ResNets already, I'm sure, if you started in your homework too, right? Hundreds of layers. And having very deep layers causes some challenges, and we'll see the cause for this challenge in a couple of classes from now when we're talking about recurrent neural networks. Then you can have things like depth-wise convolutions, where instead of multiple independent filters, we use a common layer-wise weights and combine the layers differently. So let's actually look at the depth-wise convolution, because this is a very interesting modification of your conventional filter, right? A depth-wise convolution is it's also a convolutional filter, but it's an interesting variant on the basic theme. Now, in your standard convolution, your kernel, your filter had as many channels as the input itself. So when you perform the convolution, each channel of the filter convolved with the corresponding channel of the output. And so you got one channel, one convolved channel per input channel, because every channel of the filter convolved with only the corresponding channel of the input. And then finally, all of these channels that you computed were summed up to give you the final output channel. So if you think about it, this is basically the computation that was happening, right? If I were to reorder the computation, instead of just finding the sum, the inner product over all of the layers, all of the channels of the filter at each location, I could have just redone the computation and say each channel of the filter individually scans the corresponding input channel. And then I sum them up. And the result is not going to change, right? So in terms of the computation, this is how much compute you're performing. Every single channel of the filter is convolving the corresponding channel of the input. And this cannot be avoided. Regardless of how you reorder the computation, this is how much computation you're performing, right? And so if I have 3 filters, each of these filters is going to be performing the same computation. For each of these filters, every channel of the filter is going to be convolving the corresponding channel of the input. So here, if I had, say, 1, 2, 3, 4, 5, 6, 7 input channels, then and 3 filters, I'm actually performing 21 independent convolutions. Because within each filter, each channel is convolving the corresponding input channel. So each filter is performing 7 convolutions, and there are 3 of these filters, right? So 21 independent convolutions are being performed, and their outputs are being summed up to give you 3 output channels. That makes sense to everybody? I can reorder this. Instead, I can say that I'm going to perform the channel-wise computation only once. And the only thing I will change is the manner in which I sum them up. In your conventional filter, we just simply added all of these things up, right? Instead of performing a direct addition, I can do a weighted sum. And so I can have one single filter. And the one single filter is going to have as many channels as the input itself. And now instead of summing up the convolutions that you got directly, right? So again, every channel of this filter is going to be convolving the corresponding channel of the input. So here I would be computing 7 channels, right? Instead of simply summing them up, I would do a weighted sum. And the output channels, the difference between the output channels is simply going to be the manner in which I weight the individual channels before summing them up. And so here too, I'm getting 3 output channels, but then the number of computations has been reduced by a factor of 3 because I'm doing the channel-wise convolution only once. And the weighted sum is a very trivial computation, right? And so the conventional convolution is going to look like the one to the left. If I have m input channels and n output channels, that means I have n filters. For each of the n filters, I'm going to be, if the filter size is going to be some m times k cross k, right? K cross k is the face of the filter, and it has m channels. So the total number of computations and the total number of parameters is going to be n times m times k squared parameters, right? Because you have mk squared parameters per filter, and then you have n of these filters. Whereas out here, I'm just going to have mk squared parameters. I don't have n copies of the base filter. Plus, these guys, for each of the output channels, I just have one set of weights, right? That's just going to be m weights, so n times m weights. So if you look at the number of parameters, this is nmk squared, whereas this is going to be nm plus mk squared. So in terms of the number of parameters, redoing the computation, the convolution in this manner gives you far fewer parameters. And in terms of computation, it's going to give you far lesser compute to perform. So this was the so-called depth-wise convolution, very commonly used in the past before compute became even cheaper, yeah.
Would the fewer parameters in depth-wise convolutions mean, like, does it necessarily mean a lower accuracy?
To some extent, you would take a hit, right? Again, but the trade-off is you're so much more efficient, so you're going to be able to train more, and you're going to be able to do more inference. And so that's something that we often did even in homework too, in past semesters when people were trying to run things on their laptop. Doing a depth-wise convolution meant you'd finish the homework. Doing the full convolution meant you wouldn't. Do we have any more interesting names? This one's new. Gray alligator. Who is gray alligator? Yes, first one, true or false?
The first one's false.
Okay. And teal falcon, who's teal falcon?
Here is true.
True, thank you, right? So the filters and depth-wise convolutions convolve all input channels simultaneously and sum the result. They don't sum the result, right? They convolve all of the input channels individually, and the manner in which they're summed changes from output to output. So the only difference between the output channels is the manner in which the convolutions are summed. And so they require far fewer parameters, and they require far fewer computation as a result. And so just extending to our story, you can modify these models to include invariance to other transforms. We saw that. You can make predictions related to the position and arrangement of the target object through multitask learning, and then you have other variations to get greater parameter efficiency and efficiency in computation, better ability to compute derivatives, etc. Right? So now, what do the filters actually learn? Now, going back, remember, going all the way back to when we were speaking of mammalian vision, we said that the first layer of sensors in the V1 cortex responded to specific kinds of patterns. So what kinds of patterns were they responding to? They were responding to oriented lines, right? But then when you went to the next layer, they were combining these patterns to get more complex patterns. And then the next layer still were combining these to get even more complex patterns. Now things get to be a little tricky in that, again, because neurons can compute Boolean functions, as we saw, and the Boolean functions that they can compute include the OR. And so, for example, you might find that the first layer neurons respond to things like these. So the second layer neuron might combine this and say there is a neuron which responds to a pattern like this or a pattern like this. This is an AND. But then by the time you get to the next layer, you might say this responds either to this or to this, because the perceptrons can actually perform ORs. And so as you go deeper and deeper into the network, the specific patterns that the neuron responds to are no longer going to be unique. It's going to be hard to determine exactly what is the trigger for the neuron. For the first layer, it's easy, because the first layer neurons are only going to respond to specific patterns. As you go deeper through the network, because of the ability of the neuron to perform ORs, there isn't a unique pattern that makes it fire. Yet, on any specific input, there is a trigger that causes the neuron to fire. And so you can actually go back and ask yourself, what is it that caused this particular neuron to fire? And so that's going to be and so the set of all of these is the receptive field of the neuron. And so as you go through the network, especially when you have a distributed scan, the size of the receptive field keeps changing. And here are some very interesting pictures that oh gosh, I pulled off, I forget which paper, right? So this is a network which was trained in one case to detect, I think it's the same network, but the input has different object classes, right? And so in the first column, it's been shown images of faces, where the second column has been shown images of cars, the third column has been shown images of elephants, and the fourth column has been shown images of chairs. So now, how do you find out, let's say, I have some input over here, and this is an image of a chair, and then it's gone through several layers of the network. How do you find out what portion of the input this particular neuron actually responded to? It's going to be non-trivial. You're going to actually have to perform backpropagation, and you're going to have to backpropagate to find out where the derivatives were largest, to find out which specific sub-pattern in the input the neuron actually fired in response to. For the first layer neurons, it's easy. For subsequent layer neurons, it's not going to be so easy, right? But here's what they found. When the network was shown, regardless of what the network was shown, observe something interesting about the first layer neurons. They actually obtained these oriented patterns, which look very similar to the kinds of patterns that Hubel and Wiesel found in the mammalian eye back in 1959, right? So it turns out CNNs actually end up doing something very similar to what the mammalian vision does. the whole concept seems to be a computationally capture a phenomenon very similar to mammalian vision, which is pretty impressive if you think about it. Yeah.
Well, I just wanted to know why do we want to know which neuron must have recognized that shared feature?
We don't. They're just trying to find out, just out of curiosity, right? And so they find here are the features. I mean, what is it that the neuron responds to? You're trying to find out. And they found out that when the neurons were given faces, the intermediate layer neurons responded to parts of faces like eyes and noses and such like. And then you went to higher level neurons, they actually responded to whole faces of different kinds. Whereas if these things were given automobiles, the intermediate layer neurons responded to parts of automobiles like cars, the wheels or doors. And the higher level actually responded to different kinds of cars. Same thing for elephants. The intermediate layers actually responded to parts of elephants. And then the uppermost one has elephants in different orientations. Yes?
This might be like a overly basic question, so sorry for this, but doesn't this sort of address the black box problem? Like, doesn't this mean it's somewhat explainable? We can pick apart how the neural network is working?
So yes, in this particular case, you'd have to work through, again, there's no unique trigger, right? Like I said, because of the ability to perform ORs, you can't really say there isn't a global pattern that any neuron responds to, but for any given input, you should be able to figure out which aspect of the input made it fire, right? But yes, you can get some explanations out of these, but you can see that it's actually getting some pretty good explanations, right? And as far as training, you have the standard convergence issues, Adam or other moment time style algorithms. We're going to use those in your homework, so you'll find out. We have other tricks that you can perform, like batch norm. The number of parameters can quickly get very large, and so you will often have insufficient training data, or even if you think you have a sufficient amount of training data, it will turn out that these training data don't have sufficient variety for the model to generalize properly. And so as a result, we will typically perform data augmentation. We start off with some image, and then you're going to distort it in various ways by adding noise, flipping it, rotating it, reflecting it, to not only introduce invariance to these transformations, but also to make it more generalizable and robust, right? And so we'll stop here. I have some slides later, just sort of going through the history of convolutional neural networks. Now, the modern state in AI, which is almost entirely neural network based, was unimaginable in 2011. And then in 2012, something crazy happened. We had this ImageNet challenge, where someone had collected millions of images, and there were thousands of image classes that we had to classify between. And the best systems of the day were getting something like 25% accuracy in the top 5, meaning you were considered successful if you got the correct class in the top 5 classes chosen. And then these guys, AlexNet, this was Hinton's group over in Toronto. They came up with this deep neural network based, this convolutional network based model, which for their time was so large they could not put it on a single GPU. So they had to put it on multiple GPUs. Not only was it so large that they couldn't put it on a single GPU, they couldn't even show it in the paper. So this is the actual picture from the paper. The image is cut off, right? And it had what was then considered an unimaginable number of parameters, 60 million parameters. I mean, how do you train 60 million parameters with just 1 million training instances? They went ahead and did that. And this is what changed the world, right? So we have some details of this, but what they found was, and they threw in a whole bunch of tricks that we still follow, like multi-crop. Then prior to these guys, convolutional neural networks traditionally used sigmoid activations. These guys showed that you can use other kinds of activations and it performs much better. But at the end of the day, the error rate went down from 25% to 18%, which is a huge leap, right? And If they used an ensemble of 7 networks, that went down to 15%. They knocked 40% of the error off in one fell swoop. And things didn't stop there. And they actually showed for the first time that it's explainable. They showed that the first layer of the network captures these oriented fields, much like the human eye. And then if you looked at the representations, if you looked at the confusions that it made, the confusions were often very understandable. So for example, here are things that it actually gets right. It gets a leopard, it gets a motor scooter, it gets a container ship, pretty complicated images. And when it goes wrong, it did things like this. This is actually a Madagascar cat. It's calling it a squirrel monkey. The two look very similar. In this case, the label is cherry, and the image thinks it's a Dalmatian. I don't blame it, right? So, more interestingly, if you look at the right, just before the final classification layer, you get a representation out of the network. If they used that to perform retrieval, they actually found that that representation is pretty indicative of the class. So for example, if they fed it an image of an elephant, you got some feature representation, and then used that to retrieve other images from the collection, it just almost invariably got elephants. So it was learning the classes in the representation. And of course, things took off from there. Then the next thing, these guys, just a few months later, Zeiler and Fergus reduced the error to 14.8. Then these guys in Oxford, I think, did an insane number of experiments, and they brought that error down to 7.3%. And then Google, of course, will not be left behind. So they must do 2 things. First, they must beat you. Second, they must give you a model that's not repeatable. And so they did both, and they brought the error down to 6.7%. And then someone said, I'm going to simplify things. And so that was down to 3.5%. All of this happened within a year and a half. So after a lifetime of not even being able to classify images properly, we just went from down to a situation where you can now routinely get a 1% error on the ImageNet task using a convolutional neural network. And so that's a phenomenal rate of progress, right? And that's when, for the very first time, somebody took my deep learning class. I went from having 8 students in my class, of which 6 would drop, to these classes, right? Actually, it went up to 25, and then we had to see the machine translation examples for people to realize maybe there's something to it. So anyway, and it turns out now we're using CNNs everywhere. Convolutional neural networks were 2-dimensional convolutions were initially used as a way of analyzing images. Now we do this for speech. We do this for text. I can just convert my text to a sequence of 1-hot vectors and then perform a convolutional operation on those to analyze text. Who would have thought of it, right? And so pretty much everywhere, in every aspect of any model that you're going to be using these days, there's probably some convolutional component. So it makes a lot of sense for us to understand what these things are and how they can be used, what they can do, and how we can train them. Right? In the next week, we're going to move on from convolution networks. So we're done with this particular topic. We do have one problem in the homework on how scanning with MLPs is the same as convolution. I'll do an office hour at 7 p.m. today to explain that. Any questions? Thank you, everybody.